Hi, welcome to the next class. In this class, we're going to be talking about signals. Signals are an incredibly important part of VHDL, and it's how you carry information from one part of the design to the other part of the design. Think of a signal as if it's a wire. So let's look at how we declare a signal. So signals, like we said before, are basically wires in our design. And so a signal is declared by, first off, using the keyword signal here, and then follow that with the name of the signal, and then follow that with the data type for the signal. Now, up to this point, we've said that when you're doing signals, you want to use lower camel case for declaring signal names. Let's just make that a standard for us in the class. And that helps us distinguish it from, say, a component name, which is upper camel case. And definitely helps us distinguish between a constant, which is all uppercase. And we've talked about that in past videos. So if this is how you declare a signal, and a signal represents effectively a wire, how is a signal different from a port? So if you think about a port declaration, when we did our entities and architectures, we declared ports and we gave those ports names. Those ports have modes associated with them. So a port can have a mode of an in, an out, or in-out as one of the allowed modes. We said buffer is one, but we don't really use buffer much. But those are modes. There are certain restrictions on inputs and outputs in modes and using them in your design. Now, in your architecture, you can reference any of the ports, the named ports that you want. You can reference them just like you would any other signal inside your design by just using their name. But they're different. A signal is unrestricted. In other words, when you declare a signal inside your architecture, that signal is just like a wire. You can use it as an input or you can use it as an output. It really doesn't matter. Its purpose is to carry information from one part of your design to the other part of the design. So let's see an example declaration of a signal. So here's an example declaration of a signal and a little block diagram to show us how it interconnects parts of the design. So let's say we have block 1 here. So block 1 here basically is part of our design. We want to connect it to block 2 of our design. And we need to do that by creating this signal called my connection. And that connects these two blocks together. To declare that, we would use the keyword signal, the name of the signal, followed by the data type for the signal. And that's all we need. So we can reference this name all throughout the code when we're writing VHDL and use it for interconnecting, peeling off signals, etc., or peeling off values, etc., for the design. So that's a very simple example of a signal. But signals can be a lot more complex than that. Signals can actually carry multiple signals or multiple values at one time. When we group signals together, we call those vectors. Think of a vector as a bus, like a data bus, where you take all the lines of the data and group it together and treat it as one thing. So if I have a 16-bit data bus, then I have 16 individual lines that I'm grouping together and referencing by one name, say data bus, right, or address bus. So I refer to them in one name. So the question then becomes, if you're going to do that, how do you refer to the individual pieces of that grouping, right? How do you refer to this particular wire in the group? And that's fairly easy. So let's talk about how we declare a vector inside VHDL and then what vectors can do for us. Now, first off, the declaration of the vector, it's simply use the signal keyword again. So no different than we saw before. So you can use the signal keyword followed by the vector name in this case, and it's also going to be lower camel case in declaration, followed by the vector data type. Now, the vector data type is different than a standard data type because a vector data type is a grouping, and so it's going to have a key wording at the end of the type, so to show how many bits and what their orders are. But first off, let's take a look at some of the things that make vectors unique. In a vector, you can specify a bit range, okay? So that means you can specifically name individual bits, or number them actually. You can specifically number individual bits inside a vector, by specifying a range. Typically in most digital design, you would number your bits on the left with the highest number, and the far right bit would be bit 0. So you typically start ordinal 0. You start with 0 on the right and work your way up to the other bit number. This is just standard ways of representing binary values throughout all of your digital background, right? So if you look at a binary byte, you know, and talk about bit 2, you would start on the right-hand side, that'd be bit 0, then bit 1, and then bit 2. So you're looking at the bits in the order in which they are from right to left. And that's kind of how we can do things inside VHDL. When we declare a vector, we can give numbers to the individual signals inside that vector. Now, typically, we use the keyword down to as part of that description. So if I wanted to declare an 8-bit value, right, if I wanted to do that, I would say, oh, I want this to be declared as 7 down to 0. Okay, so that would be one way to declare it. And so the bit on the far left would be number 7, the bit on the far right would be number 1. And so I've basically numbered those bits that way. It is allowed, and it is part of the standard, to declare the other way too. You can actually declare, you know, bit 0 to 7, or 7, you know, yeah, 0 to 7. So you can start low and then work your way high. This is pretty much never done because it kind of flies in the face of your standard way of bit numbering for groups of signals or vectors. So I strongly discourage even using that. Now, there might be cases where this can come in handy, but I can't think of any right off the top of my head. So predominantly 99.9% of the time, you're going to use down to, and you're not going to use the 2 there. Okay? So the other thing, the other nature about this, or the nice thing about vectors in VHDL, is you can actually specify subvectors within a vector. Let's say you've got a byte value that you put in a data vector or a data bus vector. And what you're looking to do is you're looking to get to the lower 4 bits of that vector, right? Well, you can do that with VHDL. You can say, all right, take the data bus's lower 4 bits and then put them over here. So that's a very powerful construct to be able to peel away wires from the bus. You can take a look at the least significant bit, for instance. If you're trying to detect, say, a data value, let's pretend that the data bus represents some sort of numeric value, and you want to find out if the numeric value is even or odd. Well, we would look at bit 0 for that. So you can peel off bit 0 from the bus and feed it into some other logic and use that to decide whether it's an even or an odd number. The same with sign numbers. You can use sign bits and such the same exact way. The next thing that you can do in here is you can access individual signals in the vector, not just groups of signals, not just groupings of 4, but the individual ones, just like we said before. So you can do groups and you can do individual signals. And you can also merge vectors into larger vectors. I can take 4 signals here and bring those in as the upper 4 bits of an 8-bit vector, and then take 2 signals here and bring those together, and then 1 signal here. So you have almost infinite ability to merge and create all these different combinations of signals. So just as flexible as if you were wiring it on your own board and you were taking a wire and hooking it up to this pin or that pin, you can do that with vectors in VHDL as well. So let's take a look at an example of some of these things with the vectors, so you can kind of see this in action. So if we're looking at this particular example, it's a partial example where I have 4 blocks as part of my design. And you'll notice that the output of block 1 here is labeled data bus. And the key thing about the data bus that we want to look at is the fact that right here at the bottom we specify a slash through it, a little diagonal slash line with a number next to it. And that indicates how many bits are in this particular vector. Now, that's not necessarily required, because you're going to find some vectors you're not going to be necessarily providing that particular data type, this type of vector data type. So you may not necessarily need the slash, but in most cases you'll use the slash to indicate the number of bits. It's a good information to have. Now, you can deliver that value directly into block 2 if you wish, and that's full 8 bits goes to block 2, and that can be utilized in block 2 for making decisions, you know, checking the values, passing information, whatnot. But you can also peel off parts of the bits and use it in another place. So in this case, here's an example where we're peeling off the upper 4 bits of the data bus, and we're feeding those into block 3. So the upper 4 bits are feeding into block 3. And notice the numbering here. You see the number 7:4? That tells us the range of values that I'm peeling off. So it'll be 7 through 4. So it'll be 7, 6, 5, and 4. Those upper 4 bits are going to be feeding into block 2. So that's just a graphic way of showing that. And in this particular case at the bottom, I'm peeling off a single bit, in this case bit 7, which I'm calling the sign bit, and I'm feeding that into another block in my design. So you've got lots of different opportunities for putting signals together in vectors and also peeling them apart and taking them into pieces. And that's a powerful construct. The other thing you need to be aware of is you'll notice how thick the line is when we represent a vector with multiple signals. So we use a thickness about 3 times the thickness of the single wire. But notice here, this is a single wire because it's a single bit. This is a thicker wire here, that's a single wire there. So we're showing a distinction between whether we have a group of wires or whether we have a single wire in our design. Now let's take a look at how we declare all of this. Up here, we're declaring the data bus by calling out the keyword signal, then the name of the signal, in this case data bus, and then we're using this new type, and it's called standard logic vector. Now, standard logic vector is just a way of specifying a group of standard logic signals, okay? So standard logic vector is a group of standard logic signals, and the numbering for that vector in this particular case is 7 down to 0. Now, remember, that's standard. We want to use the down to instead of the to because that corresponds to what we expect to be in the digital world, all right? So let's take a look then. Let's get rid of some of this clutter here, and let's take a look at the next declaration. So for the next declaration, we're going to create another vector called low nibble, and that's going to be 4 bits, and that's going to be a standard logic vector 3 down to 0. So we number the bits from 3, 2, 1, 0 on that one, and it's just 4 bits. And then we've got this final signal here we're going to be using, and that signal is sign bit, and it's a single bit. So it's not a vector, it's not a grouping, but it's a single bit. Now, how do we achieve this goal here? Well, we simply write a couple of commands to get that done. So number 1, block 2 can simply reference, block 2 here can simply reference the data bus value itself and pull all 8 bits in. So there's no special there. But for the high nibble, we're going to take the high nibble declaration, and we're going to take the high nibble. Oop, I found an error. That should be high nibble right here, not low nibble. So we need to fix that. There we go. So we take the high nibble and we assign it the values of data bus 7 down to 4. Right here, remember 7 down to 4. So we're assigning it those values. And that way we're pulling the 4 upper bits of data bus and assigning those to the high nibble down here. Okay, pretty cool, huh? We can do the same thing. We don't have to necessarily specify a full vector. We can do the same thing with a single standard logic signal and just assign it a single bit. Notice we only put 1 number inside the parentheses here to specify this signal down here. So we can reference it by a single bit, or we can represent it as a range of bits, okay? And so this is very powerful for creating interesting designs and making good use of the signals you have in your system. So let's take a look at, we've talked about vectors and we've talked about signals. So the next thing we want to do is we want to kind of put them to use. And so we're going to kind of segue into another grouping of data flow statements. Now we've talked about data flow being kind of a fundamental way of specifying logic. We've done an example where we use Boolean equations to define the logic for us. But now we're going to introduce two new data flow instructions. So the first data flow instruction is called the selected signal assignment statement. And this is an incredibly important statement in VHDL. It is incredibly powerful, and the synthesis engines and simulators find it very easy to generate the code for this. So it's very quick as far as turnover from logic into hardware. So this is an actually very efficient way of generating, fairly simple combinational logic, but it covers a wider range of things than you can imagine. And we're going to see a really complex example in later videos that utilize the selected signal assignment statement to achieve a really complex functionality with very little code. And that's kind of impressive, right? So when you can write code to define some very complex operation, but you do it in such a way that it doesn't take up a lot of space. So the selected signal assignment statement, just like all other statements inside the architecture, is a concurrent data flow statement. So it operates concurrently within the architecture. And it describes fundamental things like multiplexers and decoders. So we're going to look at an example of a multiplexer and a decoder here so we can see the selected signal assignment statement in operation. Selected signal assignment statements do not work inside processes. Okay, they are a architecture data flow statement. So you can't put them inside of a process statement, as most new people find out when they start trying to do the designs. But remember what we said before, it's really a bad idea to create a complex VHDL design in one giant process. That's really kind of asking for trouble and lots of debug time. So it's much, much better to plan out your design, block out the functionality, and figure out how you want it to work, and then declare the elements within it. Listen, 90% of the work of doing good VHDL hardware design is planning and design, not writing words on your editor. That's trivial. In fact, I spend at least 10 times as much time on the design, and the final stage is the easy stage. That's writing the code. That's the easy part. The hard part is making the actual design and figuring out how the signals need to work together. And if you don't do that, you're in for a lot of extra work. So that's that. So let's start with this one, though. I kind of got sidetracked there, but let's take a look at how the selected signal assignment statement works. The first thing is it starts with the keyword with, and then select is the signal you're using to decide what to do, okay? So the select signal is actually being used to determine what the output of your device is going to be, okay? So select, if the select in this case is 0, 0, then the output X will take on the value of A. So let's go down here. If I use the analogy of the multiplexer, which is basically what this is, if I make the select line 0, 0, then I'm going to pick, in this case, oops, that's flipped. Okay, so that's flipped. That's wrong. So this actually should be D, C, B, and A. So if it's 0, it will be A, and A will pass through to X that way. Okay, so if it's 0, it selects the input A and passes that out to the output. So if it's, now let's fix that again. I'll fix that on the handouts. D, C, B, and A. So basically, if you input a 1, 0, or in this case a 2, right, then the value of C should appear out. So if 1, 0 is on the select lines, then the value of 2, or the value of C should go on the output. So C feeds to the output here. So that's how you interpret this basic command. It's a simple multiplexer where the select line is being used to make a decision about which signal to pass to X. So there's inputs on the signals here, and then there's the output X here, and then the select line is used to pick which one. So it's sort of a switch, if you will. You're coming in with 4 lines, you're leaving with 1, and the select line basically controls which one you flip between, right? So this would be A and B and C and D. And so that chooses which one that you use as your reference. Okay, so with that in mind, let's take a look at another example that's a decoder example using selected signal assignment. Now, decoders are slightly different in the sense that you put in a code and then you expect a different converted code on the output. As an example of this, let's pretend that we're going to create our intro example logic using a selected signal assignment statement. Now remember, in the intro example, we have 3 input switches and we have 3 LEDs as outputs, right? So the 3 input switches' purpose is to activate or not activate, and we count up the number of switches that there are active, and then we write out to a bar display a pattern that represents those active signals. And we saw a lot of different ways to describe that. We used Boolean expressions, we used a process, we even had this crude other methodology using structured, right? So we brought in some gates and stuff and created our structure design. And so all of those are perfectly valid, but in VHDL there are tons of different ways to describe the same exact logic. And a selected signal assignment statement is actually quite a good way to describe the logic here. So if you're looking at this, we're basically, we can say that our switch inputs are being used to select. So these values over here represent the switch inputs. Now, if the switches are all off, then all the LEDs would be off, right? So these would be off. If the switches have one switch active, then one LED is on. Let's go down here. There's another one active, and it also has one LED on. If we have 2 active, we have 2 LEDs on, and there's 2 with 2 LEDs. So you can see the pattern here. So we basically created effectively a truth table where we have the inputs over here. Oops, sorry. We have the inputs over here, and then the outputs right there, right? So when the input is this, then the output is over here, and that says and that output applies to the LED signal, right? So we have switch input, LED output, it's a box, and we can represent everything in VHDL as a box in our design. And so this basically does the decoding of the number of switches. Pretty neat, right? One of the things I will point out is a good standard when you're using selected signal assignment statements to define hardware. In your block diagram, it's a good idea to just use all caps to define the block based on the name of the signal leaving the selected signal assignment statement. So since the signal is LEDs in lowercase, we're going to name it all uppercase LEDs, and that's fine for our block diagramming purposes, right? It's not part of the code, but it's fine for the block diagram. And it also helps it make it easier for us to understand, what's happening here, what signal is being modified. All right, so that's a second example of the selected signal assignment. So we did a multiplexer and we did a decoder, and that's where the power of selected signal assignment comes in. And we're going to see that we can do some really complex programs with just selected signal assignment statements, and we'll see that example in a little bit toward the end of our combinational logic discussion. All right, so the final instruction is a little more complex. I don't use it as much, but it is there and available, and it's called the conditional signal assignment statement. Now, the conditional signal assignment statement is unique in the sense that it allows you to pose true-false conditions, right? So you can basically say, if, in this particular case, let's look here, I'm checking to see if a lamp test signal is 1, right? So that's a condition, and if that condition is true, then this is the output. Oops, there we go. This is the output that comes out, right? So if that's true, that is the output. You see how that works? And so there's conditions for all signals along, or all branches of the conditional signal assignment statement. Now, this is an interesting thing to look at. It still is treated as a single concurrent data flow statement inside the architecture, but it allows for some really complex conditions inside your design. So you can create some really interesting logic just by using conditional signal assignment statement without having to go into some really complex process description. Here's an example. Oh, and the other thing is it has an implied priority associated with it, and we're going to talk about what that means. But basically it means that the first instruction is checked first, and then the next, and then the next, and then the next. And that implies extra logic. So if you have an implied priority, then you are basically introducing extra logic into your process. So you would only really want to use this in only certain circumstances. The selected signal assignment is going to be your best bet. So what I've got here is just basically a quick example of a traffic light control, right? So let's say we have a traffic light and we have, 4 lights on here. Obviously the different colors of the traffic light, we've got the green, we've got our yellow, and then we also have our red. Okay, so there's our green, yellow, and red traffic light. We're going to pretend that these values over here represent the traffic light. If it's a 1, they're turned on, and if it's a 0, they're turned off. The select input is a way to choose which light is lit. Only one can be lit, right? It's either red, yellow, or green. It would be kind of really difficult if you just lit them all up at one time, and it would be confusing in traffic. So this limits that. But we also have a extra signal called a lamp test signal that we can check to see if all the lamps are working. So let's say you're doing maintenance on this and you wanted to run a quick lamp test. You could flip a switch, lamp test switch, and see the lights, and if they all light up, yep, they're all, so a bulb's not out, right? So it gives you a way to check a bulb to see if the bulb is out quickly. So a conditional signal assignment statement will let us do this quite well. If we look here, if the lamp test happens, we light them all with 1s, right? So that happens right there. That's excellent. But if the select is 0, oh wait, let me rephrase this. If the lamp test is false, then it will go check the next one, right? So the lamp test has priority in this instruction. The lamp test, if it is true, it doesn't matter at all what the select lines are. It goes in order of the conditions listed in this instruction. So the first thing it checks is the lamp test. If the lamp test is not true, it then checks to see if select is all 0s. If it's not true, then it goes to the next one and checks to see if the select is 0, 1. In this case, if it is true, it will activate the, we could call that the red light. It just depends on how we do our bit orders here. We could activate the red light, and if it's 1, 0, it would activate the yellow light, and if it is 1, 1, it would activate the green light by doing this. Now, you may be asking, why on earth are we doing others again? You keep seeing that keyword others there. Well, the others is there for a very good reason, to prevent you from creating latches or unwanted latches, because this is a purely combinational circuit. That means that the circuit is using gates, and as soon as the inputs change, the outputs will change accordingly after a certain prop delay through the system. So this is combinational logic, and in order to make sure that you've generated combinational logic, it's generally always a good idea to use the keyword others in statements like this if your intent is combinational logic. We will see one case in state machines where we don't do the others, but otherwise you would always use others. Okay, so it's just a good practice to do. And we're going to see that more when we get into the combinational logic discussion. So that's it. This is all we wanted to do in this video, is talk about basic signals, introduce a couple of new data flow statements, the selected signal assignment and the conditional signal assignment statements. And now we're ready. We're armed and ready for some really fancy designs. But before we dive too deeply into that, let's talk about some test benching. We introduced a test bench early on in the intro, but I want to go into a little deeper introduction in our next video. So we'll see you then. Thanks.